Alright, so in this example, we are given a function, f of x, equals 1 over the quantity x plus 3 plus 5, and we need to find its inverse functions equation. We need to find the inverse function's domain and range, and we need to sketch a graph of the inverse function. So the first thing that I want to do is I'd love to do all of that for our original function f. So let's start with the domain of f. So I'm taking a look at its equation, and I notice that we've got a denominator right here, and I know that we cannot have an input that's going to cause this whole denominator to be 0. So I might go ahead and create an inequality and say, listen, this denominator, x plus 3, our input plus 3, cannot be equal to 0. So it appears that our input can never be negative 3. So we've got our domain restriction right away for our function f of x. So I might say that the domain of f of x is, well, all numbers that are not equal, all real numbers that are not equal to negative 3. And this is how we write it in interval notation. All right, now the range is a little bit tougher. For me, I sometimes like to think about it algebraically. I'm looking at this fraction right here, 1 over x plus 3. And I'm thinking, man, no matter what my input is, I'm always going to get something that's not 0 here. And when that's the case, it means this whole fraction can never be 0. A fraction is only 0 when its numerator is 0. So this is always going to be something, either a positive number or a negative number. What does that mean? Our output is always going to be 5 plus some number or minus some number. Never 5 plus 0, always 5 plus something or 5 minus something. So you know what? I think our outputs will never be 5. Impossible. There is no input we could possibly put in there and have an output of exactly 5. So I think our range of outputs, in this case, is all numbers that are not 5. So the range of our function, f of x, be all real numbers not equal to 5. Okay, well now we got to talk about what does this graph actually look like. Can we come up with some ordered pairs? Sure. No problem. Let's start with ordered pairs that have input values close to negative 3, but not exactly negative 3. For instance, I think if we have the ordered pair negative 2, or an input of negative 2, I think we'll have 1 over 1, which is 1 plus 5. 1 plus 5 is 6. So negative 2 comma 6. Now what happens? I'm going to go ahead and graph that ordered pair, negative 2 comma 6. Now what happens if we start putting in inputs like negative 1? Maybe 0. Or positive 1. You know, what are all these ordered pairs going to be? Well, if I have a negative 1 right here, this becomes 1 over 2. We get 5.5. I'm even going to write it as 5.5. I'm going to do that cardinal sin of using a mixed number. If I plug in 0, I get 1 over 3, 1/3 plus 5, 5.33. If I put in the ordered pair 1, I get 1 over 4, 5.25. And so we see a little trend going on here. 2 comma 5.25, etc., etc. So I'm going to go ahead and graph these ordered pairs. So we got negative 1 comma 5.5, 0 comma 5.33, 1 comma 5.25, 2 comma 5.25, etc., etc. And you know what? As x becomes increasingly and increasingly larger, y is going to get closer and closer and closer to 5, right? 6, 5.5, 5.33, 5.25, 5.25, 5.6, 5.7. You could go forever and ever and ever. And you know what I think that means? I think it means that we have a horizontal asymptote. Right at that point, or right at that horizontal line, y equals 5. I'm going to go ahead and draw that. Here is our horizontal asymptote, right at y equals 5. And so we know, I'm not sure what else happens with our graph, but I know that our graph is going to get real close to it, but never actually touch it. Okay, now check this out. What if I do something like something close to -3, still above -3, but not quite? What if I did -2.5? I'm going to even do this cardinal sin of doing -2.5. Well, -2.5 plus 3 is a half. 1 over half is 2. 2 plus 5 is 7. What if I did -2 and 2/3? Well, then this would become 1/3. 1 over 1/3 is 3 plus 5 is 8. -2 and 3/4, you can confirm we'll get an output of 9. -2 and 4/5, an output of 10. And so as our x-coordinates get closer and closer and closer and closer to -3, our y-coordinates get larger and larger and larger and larger. So I'm going to graph these. Here's -2.5, comma 7, -2 and 2/3, comma 8, comma 8, -2 and 3/4, comma 9. And so, as our x values get really close to -3, our y values become infinitely large. We've got ourselves a vertical asymptote. And note that this vertical asymptote at x equals -3 and the other horizontal asymptote at y equals 5 is intimately related to the fact that our domain is all inputs that are not 3, or rather -3, and our outputs are all numbers that are not equal to 5. All right, and I leave this to you to confirm, but if we used input-output pairs over here for numbers that were less than -3, we would find a similar shape on the other side of these asymptotes. I urge you to plug in numbers like -4, -5, -6, -7, and also numbers like -3.5, -3 1/3, -3 1/4, etc., etc. All right, so we've got our original graph all done. Fantastic. Now we got to find the inverse. How are we going to go about finding the inverse? Well, we got a couple of options. What I might do is first say, hey, what does this function do to its input? Well, I think that this function takes its input, and the first thing it does is adds 3 to it. The next thing our function does is it takes that quantity and it takes the reciprocal, or raises that quantity, to the -1st power. And the last thing our function does is add 5. So if we're going to try to find our inverse function, which we will do in green, the first thing our inverse function needs to do is subtract 5 from its input. So if we're going to piece together our inverse f of x, or f inverse of x, the first thing we have is an x minus 5. All right, it takes its inverse and subtracts 5. How do you undo taking the reciprocal of something? You actually take the reciprocal again. We talked about this in class. And so we can either say x minus 5 to the -1st, or we can say 1 over x minus 5. And then the very last thing we need to do is subtract 3. So you can put a subtracting 3 here, or you can put a subtracting 3 here. Here is our inverse functions equation. Now check it out. We can note a lot of things right off the bat. I'm looking at this denominator right here, and I say, you know what? I cannot have an input that's equal to 5. So I know immediately that the range of this inverse function is all real numbers that are not equal to 5. -infinity to 5, comma 5 infinity. And check it out. This range of our inverse function is exactly the same. Excuse me. This is the domain of our inverse function. Pardon me. We're talking about all inputs that we can put into our inverse function. Excuse me. That the domain of our inverse function is exactly the same as the range of our original. If our original function could never have an output equal to 5, our inverse cannot possibly have an input equal to 5. Not surprisingly, as well, that our inverse function is going to have a vertical asymptote at x equals 5. If our original had a horizontal asymptote at y equals 5, our inverse will have a vertical one at x equals 5. So I'm going to draw that right there. Let's get that a little bit more accurate. And awesome. Awesome, awesome, awesome. Not only that, for the exact same reasons that we talked about why this original could not have an output of exactly 5, our inverse function is never going to be able to have an output of exactly -3. So the range of our function f inverse of x is going to be all real numbers not equal to -3. Which is exactly the same as the domain of our original function. So we've got that domain range relationship again. Not only that, if our original had a vertical asymptote at x equals -3, our inverse will have a horizontal asymptote at y equals -3. All right, and now we got to find some ordered pairs to hopefully piece this guy together. Well, note to self, the ordered pair -2, 6, that's going to become, well, that ordered pair is going to become 6, -2. There we go, right there. So 6, -2. I'll even write that down just to catalog a few of them. All right, well, we got a whole bunch of ordered pairs. Interesting. We're going to have 5.5, -1. 5.5, -1. We're going to have 5 1/3, 0. We're going to have 5 1/4, 1. 5 1/5, 2. And you can see 5 1/6, 3. 5 1/7, 4. As x gets closer and closer and closer, or as our input gets closer and closer to 5, our output gets larger and larger and larger and larger. And you can think about that in terms of the equation as well, as we have a number that's larger than 5 for our input, but very close to 5. X minus 5 becomes a very small positive number. 1 over a very small positive number becomes a very large positive number. And that explains algebraically why we see this vertical asymptote right there. Not only that, we can find some more ordered pairs. For instance, in our inverse function, if we start inserting numbers that are greater than 5, like 6, right, I already did 6, sorry, like 7, we'll have a half minus 3, so -2.5. If I chose 8, I'd have 1 over 3. A third minus 3 is -2 2/3. If I chose an input of 9 here, well then I'd have 1 over 4. 1 over 4 minus 3 is -2 3/4, and you can see where this is going. And so, as our inputs become successively larger, our outputs get closer and closer and closer and closer to -3. And so that kind of rounds out our ordered pairs. And here we have them right here, right? These are all the reverses of all those ordered pairs, those 4 that we just talked about. And now I leave it to you. If we inserted a number such as 4, right, we'd have 1 over -1, which is -1 minus 3, is -4. So we have 4, -4, and this process is going to continue, and we're going to end up with the rest of our graph looking like this. And I mean, I'll give you a hint. You know, in general, functions that have a component to them that look like 1 over x, right here it's just a 1 over x plus 3. Here it's a 1 over x minus 5, they all have this general shape. They're just moved left, right, up, and down a little bit. And so we have the graphs of our original and our inverse. We have the domain of the original, the range of the original, the domain of the inverse, and the range of the inverse. And if we wanted to, we could compose them together as well, but that's how to take care of this type of problem. Now I'll give you a hint. On our exam, we will be given the graph of the original, so you don't have to piece it together. You may have to do some work to find the graph of the inverse, but the original will, at least its graph will be given to us.